Welcome again to the mathematical series. The task of the lecture today will be to grasp the theorem egregium of Gauss. Egregium means remarkable or extraordinary. So what is this extraordinary theorem about? The essence of this theorem is that the notion of curvature of a surface, what is called Gaussian curvature, is totally independent of the embedding of this surface in space. So we will try to understand what is behind this extraordinary theorem, which actually goes against geometric intuition, as emerging out of natural communication between the domain of harmonics and the domain of geometry. Without building encoding and decoding bridges between the domain of harmonics and geometry, it becomes extremely difficult to grasp the essence of the egregium theorem of Gauss. So, let's start by recalling what we have achieved up to the previous time, where the central notion is synchronization as the obstacle which appears from the domain of harmonics. And it is this obstacle now of synchronization which we have used repeatedly, for example, in the proof of the Pythagorean theorem, or in order to understand the relation between the circular domain and the linear domain, the problem of rectification of the circle according to Archimedes through the Archimedean spiral. All these things revolve around this notion of synchronization. And this notion is not emerging from the geometric domain, but it is emerging from the domain of harmonics. And just to recall that the natural communication scheme now between harmonics and geometry in this setting, which actually is rooted in the proof, in the abductive proof of the Pythagorean theorem through the annulus, which is formed, as we have explained, by an orthogonal triangle. The encoding bridge from the domain of harmonics to the domain of geometry consists in the translation and rotation of the tangents, as you can see here. So the tangent is this side of this Pythagorean orthogonal triangle, about which we think as a velocity or as a momentum, which is doing two motions. In contrast with this side, the orthogonal side of the right triangle. So the velocity rotates, but at the same time translates around the circumference of the circle, which has as a radius the other orthogonal side. And it is bounded by this bigger cycle, which is formed by a rotation only of the hypotenuse. So the encoding bridge is the translation and rotation of the tangents, of the velocities. Through this, the Pythagorean theorem now gives rise to a partition spectrum. This is a spectrum of areas, and it involves the universal constant pi, which pertains to the characterization of both the perimeter and the area of a circle. In the domain where we have this spectrum of areas, our thinking takes place in geometry. So it is the level of geometry. We need the decoding bridge to go back to the harmonic domain in order to achieve synchronization, and the method is the harmonic parallel transport of all the tangents. Here we have the picture. So as soon as we obtain this annulus, according to our previous lectures, we harmonically parallel transport all these tangent velocities to a joint center of synchronization. And in this way, we obtain a disk. So the area of this annulus, about which we think as a partition spectrum of different colors, is equal with the area of this disk. It's important to pay particular attention that this disk here is a disk in the momentum space, since the radius of this disk, it is formed by all the tangent velocities, and because of uniformity, all these tangent velocities have the same length, and this is why we obtain a disk. The center of this disk now, since all these velocities are of the same length, is identified with the center of synchronization. And this is how the communication between the domain of harmonics and geometry takes place. Now, if we think of this setting here, but we consider it as a screen which is coordinatized in terms of the complex numbers through the complex exponential function, then the communication between harmonics and geometry is characterized by a particular cipher. And this cipher, which comes out of the extension of the exponential function from the real line to the circle, identified with the unit circle on the complex plane, says that the exponential of 2 pi yod, the imaginary unit, kappa, where kappa is the winding number, equals 1. And please pay special attention to the fact that this universal cipher characterizing the domain of communication between harmonics and geometry is expressed in terms of this pi. So this is now this domain of communication together with this universal cipher that we consider that it determines out of natural communication this universal geometrical constant pi, which characterizes the Pythagorean spectrum of areas, for example, in the case of the circle. So in this way, we think of this constant pi as a tuning parameter between the domain of geometry and the domain of harmonics. So we grasp this constant pi, which basically appears in the first time in the characterization of the perimeter of the circle, but now in relation to the domain of harmonics as a tuning parameter. And it is the unique constant which gives rise to this universal cipher. So this is how we understand, not only from the domain of geometry, but out of bringing these two domains in communication to each other and in relation to the obstacle of synchronization, the tuning parameter pi. Now, this is what we will use in order to grasp the essence of the extraordinary theorem of Gauss. This theorem says that the notion of curvature of a surface is independent of bending this surface into space, is totally independent on how we put this surface into geometric space. So the curvature is an intrinsic characteristic of the surface itself, totally independent on how you embed a surface into space. The fact now that the curvature is independent of the geometry of the space where a surface may be embedded is a clear indication that the notion of curvature should be related with the tuning which is achieved through this constant pi. And we think of this tuning in terms of the notion of a circle. And we will see how this notion of a circle, but as a tuning parameter, plays this particular role in relation to the curvature of a surface. So let's keep in mind the Pythagorean annulus, where we have rotation and translation. We think of rotation in relation to architecture and translation in relation to mechanics. We have already explained the relation between these two by using the complex exponential function. We keep in mind that the area of the disk, which is swept out by velocities, which are synchronized here, is an area of a disk in the space of velocities, in momentum space. So if the annulus, which is formed by rotating an orthogonal Pythagorean triangle, is thought of in position space, then the disk of synchronization should be thought of in the space of velocities, in the momentum space. And these two spaces are not identified, although we can obtain the area of the annulus by the area of the disk geometrically. We also keep in mind the rectification of the circle according to Archimedes. So we will need to combine all these notions that we have up to now in order to grasp the essence of the theorem egregium of Gauss. I just remind you that the Archimedean spiral is a bridge between the circle and the unrolling of this circle as a line through the tangent after a complete rotation of the spiral. So the spiral is not an operational geometric object, but is a bridge between the circular domain and the linear domain. In this way, we manage to unfold the circle into a straight line through the Archimedean spiral, such that all the area of the circle is encoded in the area of this orthogonal triangle, which is brought along at each stage of unfolding the spiral. And the next thing that we'll keep in mind is what we have already discussed from the perspective of our screen, coordinated now through the complex exponential function in terms of the imaginary and the real numbers, so the complex numbers. And it is this helix here as a universal covering of the underlying circle. Here you can also think again of the annulus that we get through the Pythagorean theorem. And the phenomenon, the new phenomenon that we have here is that the inversion of this exponential projection from the real line, but this is the real line now in quantum space, as we have already explained. So the helix is the real line in quantum space. So the inversion of this exponential function, so what we call the complex logarithm, brings along the notion of branching in space, and the notion of abducting area from space into time through the windings of this helix. So the logarithm is only locally inverts the exponential projection from the universal covering, so the helix, to the underlying circle on our screen. So keeping this thing in mind, we go now to recall one more thing that we will use, and this is, of course, the catenary curve, the natural curve of a hanging chain under the influence of gravity. And recall that this was the starting point of conception of calculus by Leibniz, and it can be thought as the arithmetic mean of this exponential curve here and its mirror image with respect to the vertical axis. So this is the catenary curve, and it is formed as an arithmetic mean of the real exponential e to the x, okay, where x is this axis here, plus e to the minus x. And since we have arithmetic mean, we have to divide by 2. Now the curve we get is this catenary curve. Okay, let's now try to see where the notion of curvature comes from. We do not want to consider the notion of curvature ab initio as something which is given geometrically. If we pay particular special attention to the extraordinary theorem of Gauss, first of all, we have to figure out where curvature comes from. We do not want to consider it through the embedding of a surface into geometric space. Our instrument is the screen. So we use always a screen about which we do not think as a two-dimensional plane. The screen has always a projective nature, so it is a projective space. All the qualifications we have given up to now pertaining to the Pythagorean theory, to the rectification of the circle according to Archimedes, to the catenary of Leibniz, they all of them involve a screen. So we will want to continue in the same motif, and we want to gain an understanding of what the curvature is about from the projective point of view of a screen. Now, if we consider the technology of the complex exponential function, so we work with the complex numbers, so the real numbers are on the horizontal axis, and the imaginary numbers are on the vertical axis, perpendicular to the real one, as we have already made the construction. Then we want to think of the screen of this disk now, which is bounded, let's say, by the unit circle in the complex plane. So this is the unit circle in the complex plane. And we have already explained how these sectors here can be thought in terms of what we have called the roots of unity on the complex plane and thus on our screen. We want to think of this as the projection of a sphere. So the idea is that since our screen is a projective object, this projection here, coordinated in terms of the complex numbers, is the projection which is emerging by a sphere. In this manner, we think of our screen in terms of light. The idea is that what is called the stereographic projection, which makes our screen a projective object, not a two-dimensional plane which is embedded in space, but a projective screen, which gives what type of information? Gives always a type of information according to some invariant. This is the abstraction which makes this projection possible. And this is rooted in the thinking from astronomy, of course, of Hipparchus, the first great astronomer, and Ptolemy. And it has been called the planisphere projection, what is known today as the stereographic projection of the sphere. Now, why we have to think of this projection in terms of light? The reason is the following. We consider that here is the north pole of the sphere, and we consider light rays which are coming from the sun. They pass through the sphere and they are projected on this screen here. The characteristic now of this projection is that it is a conformal projection. Conformal means that it is preserving oriented angles. So, if we consider For example, a circle on the surface of this sphere, and we consider the angle which is formed by a tangent at any point of this circle and any other line, then on the projection, this angle on the screen will be exactly the same in magnitude and in orientation with the angle of the circle on the sphere. As an outcome from this conformal characterization, we obtain that circles which do not pass, of course, from the point of projection, but they can pass from any other point, are projected as circles again on our screen. And this screen now is coordinated in terms of the complex exponential function. So it is coordinated through the complex numbers. The invariant of this projection is the angle. Whatever angles we have on the surface of the sphere, all these angles are preserved on the projection. But although all angles are preserved, and as a result, all circles not passing through the center of projections are also preserved, as you can easily see, all areas and all distances measured on the surface of the sphere are very badly distorted on our screen. This is now the indication that there is some invariant characteristic unique in relation to the sphere. The reason is that if this characteristic, which is actually the characteristic that we will call curvature, if this characteristic, this invariant, did not exist in relation to the sphere, then not only angles would be preserved, but also areas and lengths, as of course it is the case for a planar surface. Now this is the way to start thinking about the notion of curvature. And if we want to go a step backwards in relation now to this natural communication between the domain of harmonics and geometry, we recall that the basic thing is the translation and the rotation of the tangent in the encoding bridge from harmonics to geometry. So, the idea is to start thinking about this unique characteristic of the sphere, what we will call curvature, through rotation and translation of tangent velocities on the sphere. In particular, it will turn out that the curvature of the sphere can be characterized as the rotation of the tangents per unit area. So we think we will see how this is possible, but we think of the curvature, this particular type of bending of the sphere in relation to the rotation of the tangents brought into proportion with area. So we have rotation per unit area will be this aspect that will be characterized as curvature. Recall now that beyond the stereographic projection of the sphere, here we have another projection. It's the projection of Archimedes, the radial projection of the sphere. It is again a projection on a screen, but this screen now is different from the previous one. This screen, which is given by the cylinder, the idea of Archimedes is to put the screen inside a cylinder. And in this way, to determine what is called the equiareal projection of the sphere. So to find a projection of the sphere which will preserve not the angles, as in the previous case, but the area of the sphere. The idea is that this screen comes from the projection, the radial projection of the sphere onto a cylinder, and of course the cylinder can be unrolled on a flat surface. So this unrolling gives rise to a projection screen, but this now is a projection screen which preserves only the area of the sphere. This was the construction that we have already made, where we have showed through the rectification of the circle by Archimedes that the area of the sphere equals to the area of 4 disks of equal radius. So this is now the screen which preserves the area of the sphere, but does not preserve the angles as the conformal or stereographic projection. The fact now that these two projections, one in relation to the angles and the other, the Archimedean, in relation to the area, means that there is some intrinsic invariant characteristic of the sphere which is different from the plane, because in the case of a planar surface, we preserve both the angles and the areas. This is not possible in the case of the sphere. So our screen, either we will preserve the angles or it will preserve the areas. Now, if you think of the angle in terms of rotation of the tangents, the in-between these two types of projections, what is going to give rise to an invariant characteristics is the rotation per unit area. So rotation in relation to the notion of the angle which is formed by the tangents, and area in relation to the equiareal projection of Archimedes. If we bring these two projections into proportion, so we think about rotation per unit area, we get out of this ratio, out of this proportionality relation, an invariant characteristic of the sphere, which is the curvature pertaining to the sphere. And now the thing is that the curvature of the sphere, and of course, as we will see, not only of the sphere, but of any other surface, is totally independent of how the sphere is embedded into space. So it doesn't have to do anything at all with the embedding of the sphere into space. This is what makes the curvature an intrinsic characteristic of the sphere itself, independent of the surrounding space where we may think of the sphere as being embedded. So through these two projections now, the projection of Ptolemy and the projection of Archimedes, bringing them into proportion, so try to make a kind of ratio between these two different screens, the first preserving angles and the second preserving areas, we arrive out of this abstraction to the abduction now of the unique characteristic, the unique invariant of the sphere, the curvature. What we want to see now is how this relates with the notion of tuning. So, is there a way to obtain the notion of curvature using the tuning which is emerging out of pi? We think geometrically always of the pi in relation to the perimeter of the circle. So the idea now is that we want to express the invariant characteristic of curvature in terms of a tuning, in terms of circles. This is the notion of an osculating circle. This notion appears, first of all, I would say in Leibniz, but it also appears in the thinking of Euler and eventually in the thinking of Gauss, through which he expressed his egregium theorem. So we think now, consider an arbitrary surface, not necessarily the surface of a sphere. The idea is that we can consider at each point of this surface what is called an osculating circle. Osculating circle can be thought of as a rolling circle. Rolling pertains to rotation and translation, so it's fully in accordance with the encoding bridge from harmonics to geometry. And the idea is that an osculating circle is best approximating the surface at any point of this surface. So, at any point of the surface, I find a circle which fits at this point. So, the curvature of this surface, the local curvature at any point, is thought of in terms of a circle which is tangent at this point to the surface. And in this way is best approximating the surface at this point. Of course, in the case of surfaces, like in the case of a sphere, we have to consider an osculating circle with respect to two directions, the directions of our screen. The idea of Gauss now is that in rolling around, so rotating and translating, an osculating circle being tangent at each point of the sphere went up with two principal magnitudes. The idea is that the curvature of the surface should be expressed in terms of the radius of the osculating circle, where under this rolling around there are two extreme cases, when this circle becomes minimal and when the osculating circle becomes maximal. Of course, the osculating circle, being tangent at any point, it has a radius. So the curvature is expressed by the reciprocal of this radius. So these extremal cases, what are called the principal curvatures of this surface, if we roll around an osculating circle, we will find out that these radii now are in orthogonal directions. So we can think of them in two ways. By taking the arithmetic mean of these two, so by forming the mean curvature, an approach which leads to the notion of a minimal surface, where a minimal surface is a surface which encloses the minimal area. As we will see later, this is the catenoid made out of the catenary curve as a surface of revolution. And we can also take the geometric mean of these principal curvatures in these orthogonal directions. So the tuning, the idea of the pi tuning now, which is the method that we use in order to abstract the invariant of curvature out of the relation between harmonics and geometry, is this notion of the osculating circle and the fact that under rolling around, so under rotation and translation, we have two extremal values. These determine the principal curvatures and the radii of the circles at the minimal and the maximal case. They are orthogonal to each other. Let's see now how this works in the case of a sphere. So in the case of a sphere, if we consider this point here, we have the osculating circle, which you see here through these arrows pointing downwards, because we want to keep track of the direction and orientation. And you have in the perpendicular direction another osculating circle here, which in the case of the sphere, of course, it has exactly the same radius. So the minimal and the maximal case in the case of the sphere, they are clearly the same. They are both great circles passing through this point, and they are also directed in the same way. So from this osculating circle, we have a radius of curvature, which is the radius of this osculating circle, equal to the radius of the sphere, and also we have the radius of this great circle, which is also an osculating circle, and it has also the same radius. So the product of these two, and since they both point to the same direction, the product is positive, and the reciprocal of this product gives what is called the Gaussian curvature of the sphere. Now, the Gaussian curvature is precisely the invariant which characterizes the sphere independently of any embedding of the sphere in space. So it is a unique invariant characteristic of the sphere itself independently of embedding the sphere in space. So the Gaussian curvature of the sphere is simply the reciprocal, 1 over r squared. Now the tuning happens in terms of these osculating circles. Since now the Gaussian curvature of the sphere is intrinsic to the sphere and it's also positive, we have, of course, the most characteristic case of positive Gaussian curvature in contrast to the zero curvature of a planar surface, of a plane, where there is no bending at all, and of course it has zero Gaussian curvature. So the sphere is distinguished from the plane, and of course, not only from the plane, but from any other surface which also has Gaussian curvature 0, because it's not only the plane. For example, the cylinder has also Gaussian curvature 0, is distinguished by the fact, so the sphere is distinguished by the fact that it has positive Gaussian curvature. And this Gaussian curvature emerges out of tuning in terms of the principal curvatures of the osculating circles at the extreme cases, min and max, where in the case of the sphere, they are exactly the same. They are both great circles of the sphere. Here, we have a different case. And we focus in this case because these three cases, positive Gaussian curvature, zero Gaussian curvature, and negative Gaussian curvature, as in the case of this saddle surface that you see, are all the types of curvature. So if we think that the invariant of curvature gives rise to a partition spectrum of all surfaces, with respect to this intrinsic characteristic, there are only three cases. The case of positive curvature, with the most characteristic example, the case of the sphere. The case of zero Gaussian curvature, with the most characteristic, the case of the plane. And the negative Gaussian curvature, with the most characteristic case now, the case of the saddle. The idea is that the negative Gaussian curvature here is also emerging out of natural communication between harmonics and geometry. So, in terms of tangent osculating circles, which, what they do a tuning at each point of this surface in relation to the constant pi. The key again is that the constant of Archimedes, pi, is a universal constant irrespectively of the radius of the circle. But by rolling along and across an osculating circle to a surface, we are tuning this surface in terms of the irrational number pi, and of course the radius of this circle. And the extreme cases will give rise to the principal curvature. Out of this, we can form the geometric mean of these principal curvatures, or simply the products of them. And out of this product, we will get the invariant characteristic as given by the remarkable theorem of Gauss. But now the truth of the theorem is abducted simply by tuning the surfaces in terms of osculating circles. So the idea is that any surface can be tuned with respect to an osculating circle which is rolling around the surface. This rolling will give rise to two extreme cases, the minimum and the maximum, and then through the geometric mean of these two values, or simply the product of these two values, we get what is called the Gaussian curvature of this surface. So let's see how this works in the case of the saddle. And we consider the most characteristic point that you see here in this picture. So we have an osculating circle which is directed in this way, so it fits to this context of bending, and we have another osculating circle which is directed in the opposite way, and it fits in this context of bending of the saddle. These two cases now are, of course, again, as in the case of the sphere, the min-max cases. But because now the osculating circles, so the tuning that we do through rolling by an osculating circle, they are directed in an opposite way, the product of them, if we take care of the signs, so if we consider this as a positive and as and this one as the negative one, so this as the positive orientation, and this as the negative orientation, the product will be negative. And since the radii of these two circles, of these two osculating circles, is the same, we get a constant negative curvature of -1. So, if in the case of the sphere, okay, in the case, of course, of a unit radius, we have positive Gaussian curvature 1. In the case of this saddle here, the tuning by osculating circles, so tuning by the irrational transcendental parameter pi, gives rise to a constant negative curvature. And of course, the case of the plane is the middle case between these two, where the Gaussian curvature is 0. The next thing now is to try to figure out how the surfaces of negative Gaussian curvature emerge. And the reason that we are interested into this is that because the cases of negative curvature, what are called as hyperbolic surfaces, in contrast to the spherical surface, which has positive Gaussian curvature, they are related in an intricate way with the catenary. So this will be the task that we will have next time, to understand the theorem egregium of Gauss for hyperbolic surfaces in relation to the catenary curve.